This video demonstrates how to work out a limiting reactant problem from a first semester chemistry class. The main target audience for this would be college level chemistry, but I know that some high school instructors also cover these sorts of problems. First, let's take a look at a question that might be given. Given 5.00 grams of aqueous sodium carbonate and 5.00 grams of hydrochloric acid, determine A, the limiting reactant, B, the excess reactant, C, the theoretical yield of gaseous product. That's a hint that one of our products, at least one of our products, has to be a gas. And D, if 1.53 grams of the gaseous product is actually obtained, determine the percent yield. Okay. Well, there are many issues involved here. By being given the names of the substances and words, that's a quiz on your chemical nomenclature. Do you know how to write the formulas properly for sodium carbonate and hydrochloric acid? If a person knows how to convert the name sodium carbonate into a formula, they'll get that. That will be a subject of a different video before this one. And in a similar way, hydrochloric acid would have this formula. What I'm slowly developing here is a balanced chemical equation, because to answer questions like Part A and Part B about the limiting reactant and the excess reactant, we need to carry out stoichiometry. And stoichiometry requires a balanced chemical equation so you can do conversions in moles. Alright, now to figure out the products, whenever you're not given them, we would need to know the building blocks of these reactants. For example, sodium carbonate can be thought of as a combination of sodium ions with carbonate ions. Oh, I forgot my state symbols. They mentioned in the problem that the sodium carbonate is aqueous, and when they use the name hydrochloric acid instead of hydrogen chloride, that can be interpreted as implying aqueous. So I put the aqueous state symbols on those two. Okay, now we can see the breakdown of the sodium carbonate. It can be thought of as sodium ions combined with carbonate ions, and I wrote the formulas below. And in the same way, the hydrochloric acid can be thought of as a combination of hydrogen ions and chloride ions. And I also wrote those formulas. To get started here, we'll presume that a chemical reaction does occur. That would mean that the carbonate ions are no longer with the sodium ions. They must be with the other positive ions, the hydrogen ions. And that would leave the sodium ions with the chloride ions. So this scratch work on the right side would be H plus ions are going to be combining with carbonate, and Na plus ions are going to be combined with chloride. To balance a carbonate ion with hydrogen ions, the carbonate ion is -2, the hydrogen ion is +1. Those charges do not balance. So we would need two +1 hydrogen ions to balance the carbonate ion. So our first product would be H2CO3, if we could get that. So there's a problem there, but that we'll come back to in a moment. In a similar way, a sodium ion is +1 and a chloride ion is -1. One of each will balance each other, so we get NaCl as the formula. So an important thing to realize is you have to balance the charges first before you can balance the entire equation. Okay, so what I see here is that there's two sodium atoms on the left side and only one on the right side. That's a little bit of a problem. So let's write an AQ symbol on the sodium chloride. Let's say that we don't know the state symbol on the H2CO3 because that's the problem. A lot of people are going to assume that we get that gas because of the wording of the problem, where it's talking about a gaseous product. That is not actually correct, but we'll come back to it. Oh, well, let me talk about that right now. When I took chemistry class, we were given a list of certain substances that you cannot get as a product. Instead, when you try to form certain substances, they decompose, and H2CO3, carbonic acid, is one of those. Below my main equation here, I've written a smaller equation showing what happens. Carbonic acid actually decomposes into water and carbon dioxide. So if I try to balance those sodiums like I was about to do a moment ago, the two sodiums on the left would not balance with one sodium on the right unless I put a 2 in front of the formula for sodium chloride. Now that messes up the chlorine atoms. I now have 2 of them on the right, but there's only 1 of them on the left with the HCl. So to balance that, I'll need to put a 2 on the HCl. And I had to shrink my font to fit it on the line. Sorry about that. Now at that point, it looks like there's 2 sodium atoms on both sides. There's 1 carbonate ion on both sides. There's 2 hydrogen atoms on both sides. And there's 2 chlorine atoms on both sides. So that seems to be a balanced equation. But we still have the problem of the H2CO3 hanging over our heads. It turns out that that can be thought of as an aqueous acid. So I'll write the AQ state symbol on the H2CO3. But we actually cannot get that. We're supposed to get a gaseous product, so the problem was hinting around that we actually have that H2CO3 decompose. So according to my smaller equation on the bottom, 1 of these moles of H2CO3 will actually make 1 mole of liquid water and 1 mole of carbon dioxide gas. Therefore, we can replace H2CO3 in the main equation on the product side with H2O liquid and CO2 gas. And now our balanced equation looks like this. So we had to do all of that just to begin working on part A. But this is normal. We have to balance our chemical equations in this class. So at this point, I'm ready to use that equation to do some calculations. The reason I'm doing a slideshow is because my handwriting tends to get sloppy when I'm trying to get a lot of work done, because I try to get it over with. So I'm using slides here for clarity, to make it easier on the eyes for anyone watching. But if I was writing this by hand, the first thing I would do is write down the 5 grams of Na2CO3 and the 5 grams of HCl that we were given. That would look like that to get it started. In each case, you can't use grams. These balanced chemical equations only convert moles. So what I'm going to do is convert grams of sodium carbonate into moles and convert grams of hydrogen chloride into moles. I presume that you know how to use the the periodic table to find the formula mass or the molar mass of those 2 substances. When you do that, you will get the results that I'm about to plug in here. On the first line, we cancel grams of sodium carbonate on the bottom and come up with moles of sodium carbonate on the top. So this is just a conversion from grams to moles. On the second line, we also convert grams of hydrogen chloride into moles of hydrogen chloride. And we can run those through a calculator and get some results there. 0.0472 moles of sodium carbonate was given to us in the problem. And 0.137 moles of hydrogen chloride or hydrochloric acid was given to us. Now we still haven't answered part A, which was asking about the limiting reactant. What we'll do is we'll take one of these initial amounts and convert it into moles of the other substance. For example, we could take the moles of HCl and try to find out how many moles of Na2CO3 would be needed to use up all of the HCl. So to get started, I'll use the 0.137 moles of HCl, and then these numbers are 2 moles of HCl for every 1 mole of sodium carbonate. Those mole numbers came from the balanced equation. No number on Na2CO3 was a 1, and the 2 on the HCl was the 2 moles of HCl. So the result from that calculation is 0.0686 moles of Na2CO3. When I ran it through my calculator, I had extra digits in there, and so I'm rounding from what actually appeared on my calculator, not from using 0.137, but using the numbers that were actually on the calculator when I got the 0.137. At any rate, we could compare the moles of Na2CO3 that I just got to the moles of Na2CO3 that we were actually given. I would need 0.06 moles of sodium carbonate to use up all of the HCl, but we were only given 0.04 moles of Na2CO3. From that, we should conclude that we're going to run out of the Na2CO3, the sodium carbonate. And what does that mean? There's not enough sodium carbonate to use up all the hydrochloric acid. And that actually answers part A for us. Part A, the limiting reactant is sodium carbonate. Now there's only two reactants, so if the sodium carbonate is our limiting reactant, then the other reactant, the hydrochloric acid, is our excess reactant. So that answers question B. So let me free up some room here. What I'm going to do is keep my first line of work, where I calculated the moles of the limiting reactant, the moles of sodium carbonate. But I'll record my answers for part A and part B. So there we go. Part A was the limiting reactant, part B was the excess reactant, and what I've done is I've left here my line of work where I calculated the moles of that limiting reactant. Why did I do that? Because you're supposed to use the limiting reactant to perform all the other calculations in a limiting reactant problem. Like what? Part C. What's the theoretical yield of the gaseous product? Well, our products were liquid water, carbon dioxide gas, and sodium chloride aqueous. Well, the only gas there is carbon dioxide. So somebody's asking us to calculate the theoretical yield, which is usually a mass in grams, of the carbon dioxide, but they were trying not to give anything away by not mentioning carbon dioxide. All right, well, we take the 0.0472 moles of sodium carbonate and we try to convert it into moles of carbon dioxide using our balanced equation. The first step of that would look like this. 1 mole of sodium carbonate converts to 1 mole of CO2 product. And then while we're at it, we might as well use the periodic table to convert moles of carbon dioxide to grams. 44.01 grams of carbon dioxide per every mole, according to my calculations on the periodic table. When we run that through a calculator, that would give us 2.08 grams of carbon dioxide, and that would answer question C. That would be our theoretical yield of gaseous product. So let me record that and wipe out our work here to create some room for part D. Part D, if 1.53 grams of gaseous product, they mean gaseous carbon dioxide, is actually obtained, then determine the percent yield. Well, there must be a formula for percent yield. If we look that up or if we have it memorized, percent yield is actual yield divided by theoretical yield and then times by 100 to make it a percentage. We know the actual yield from the question in part D. They told us it's 1.53 grams was actually obtained. But what's the theoretical yield? We found that in part C, 2.08 grams. So if I plug those two in, this formula becomes 1.53 grams divided by 2.08 grams times 100. And that would give us 73.7% yield. And that gives us the answer to part D. Our percent yield is 73.7%. I hope you found that helpful. If you'd like to thank me by making a donation to my PayPal account, I've provided a link below the video in the description. If you're interested in hiring me for an appointment, or visiting my live stream where you can get help with a single problem at a time instead of hiring me for an entire hour at a time, my Twitch page is located at the link provided in the description below the video, as well as my Facebook page. Information about prices, including the amount that I charge per hour and group rates, and also the amount that I charge per problem, and the live streams is provided at those locations. To actually schedule an appointment, you can contact me directly by email. And I thank you for watching the video.